Okay, this is a continuation of the practice test for Mac 1140 Pre-Calculus, Chapter 12. We now continue with numbers 31 through 45, which were the problems from section 12.3 concerning geometric sequences and series. So in number 31, they give you this rule in order to create the terms in the sequence, and you are to determine whether it's arithmetic, in other words, it has a common difference between the terms, or whether it's geometric. Those have a common ratio between the terms, or whether it's neither. So if you're going to get the very first term using this rule, you would just go 7 minus 3/2, and you would plug your n equal to 1 right in there. So this ends up being 7 minus 3/2, or 7 minus 1.5, but you can stick it in just like this, and you should get back 5.5 in your calculator. You can also make your calculator keep it as a fraction. Instead of hitting equals right after you enter 7 minus 3/2, you would hit math, enter, enter, and it'll give you the fractional form of this if you prefer to do it that way. Okay, moving on to n equal to 2, you should generate a few terms in the sequence and then decide whether it's arithmetic, geometric, or neither. If you're going to go and evaluate this at 2, it would be 7 minus 3/2 times 2. You're putting a 2 in for n. In this case, the 2's would cancel because this 2 is the same thing as 2 over 1. So you would actually have 7 minus 3 is all that would be left. So this is equal to 4. Okay, so far this has generated a 5.5. Then the next term in the sequence is 4. And I'm going to do one more. It should be enough to have 3 terms. So it would be 7 minus 3/2. This time you're plugging in a 3. So this would be 7 minus 9/2. You could pop that in your calculator. And 7 minus 9/2 would be 2.5. Okay, so this would be the next number in the sequence. And it goes on. So now what you want to see is what you want to answer whether this is arithmetic or not. If it's arithmetic, you'll have the same difference in between each of these terms. Now to get from 5.5 to 4, you need to subtract 1.5. You would have to subtract 1.5. Now if the same number is used to go from 4 to 2.5, then it's arithmetic because you're repeatedly using the same number to either add or subtract. We call it addition if it's a positive number, and you can refer to it as subtraction if you want to for a negative number, or you could just say you're adding a negative number. So from here to here, you would have to subtract 1.5. You see that it is the same, and you can put that in your calculator, just 4 minus 2.5, and you would see or actually 2.5 minus 4, and you would see it's a negative 1.5. So you're going down by 1.5 each time. When you're going down, it means you're subtracting. Therefore, this is arithmetic. Arithmetic sequence. Okay, so on your practice test, you should have printed out the practice test and simultaneously be looking at it as I go through these answers, so that you can follow along with the choices. So it is definitely arithmetic, and the common difference, they want you to find the common difference if you claim that it's arithmetic, and that common difference is negative 1.5. If you want to give that as a fraction, this is 1.5, which is the same thing as 3/2. They never give them as mixed numbers. They either give it as an improper fraction or you can give it as a decimal. So that would be choice C. Okay, moving on to 32. In problem 32, it's the same set of instructions. You are starting off with this rule in order to generate the terms in the sequence, 5/4 raised to a power of n. And you're going to try and decide whether the numbers created by using this rule, whether they are arithmetic, geometric, or neither. Okay, so for n equal to 1, in other words, you're putting a 1 in there, it will be 5/4 raised to a power of 1, which is just 5/4. So first term in the sequence is 5/4. Then if you're going to let n be equal to 2, then you would have 5/4 raised to a power of 2, and that would be 5 squared is 25, and 4 squared is 16. So this would be the next term in the sequence, and I'm going to do one more. Okay, if you allow n to be equal to 3, then it's 5/4 raised to a power of 3. That would be the same thing as 5 cubed, and you can put that in your calculator. 5 cubed on the top and 4 cubed. This power belongs to the top as well as the bottom, just like this power belongs to the top as well as the bottom. So let's see, let's make this a little bit bigger. So when you go 5 cubed in your calculator, you get 125, or possibly you know it in your head, and 4 cubed would be 64. So that would be the next term in the sequence. So now, if this is geometric, it doesn't look like the same number could be added to get from this to this and from this to this, but it's possible that you may be able to multiply each of these fractions by the same ratio in order to get from term to term to term. So I believe what would work in this particular case would be, let's see, if I want to turn this into a 25, and you know that it's multiplication that's required, multiplication by a common ratio to get from term to term, I'd have to multiply this by 5 to turn this top into this top. And if I wanted to turn this into this, I would have to multiply 4 times 4. So this times this would be 25, this times this would be the 16. So this would be the common ratio, but you need to check to see if it works for the next one. If I was to multiply this by 5/4, it would give me 125. 25 times 5 is 125, and 16 times 4 is 64. So it works here as well. So the common ratio here is that multiplier that gets used repeatedly to move from term to term to term. And this is geometric. When it's a common multiplier, common ratio multiplier, it is considered geometric. And then I just showed what that common multiplier was that would get you from term to term. When it's a common difference, in other words, you're either adding the same number to get from term to term or adding the same negative number, which can also be listed just like this, then it's arithmetic. Okay, so that is 32. Moving to 33. In problem 33, they give a sequence like this. Instead of the rule, they just list the numbers for you. And we're going to decide if there's any kind of geometric or arithmetic properties for this particular sequence. So let's see. Let's say that I was concentrating on whether or not it's arithmetic. I would be looking to ask, hey, what number do I add to each number to get to the next number? Well, from here to here, you'd have to add 2. But then to get, and it has to be a consistent 2 that's added each time. But yet you already break that here because now it's something different. So because it's not the same value that needs to be added as you move from term to term to term, it is not arithmetic. Okay, let's see if it's possibly a common multiplier. What could you multiply this by to turn it into a 4? You can multiply by 2, but the minute you go and multiply by that same number, you do not create a 7. So it is not geometric either. Because you don't have a common ratio. And it's not arithmetic because you don't have a common difference. Okay, so we have to say that this one is neither. And let's pick out the choices that were these answers. In 33, the one that I'm on right now, that would be choice D. And then the choice for number 32 that had both of these answers, geometric, and 5/4 says the common ratio, that would have been B. Okay, moving to 34. And in problem 34, 34 through 36, they're asking for the 5th term and the nth term of the geometric sequence whose initial term A, so when they talk about A, they're really talking about A sub 1, the very first term, and common ratio R are given. So in 34, they tell you that A is equal to 5, which is really A sub 1, the first term. They just happen to call it A. And the common ratio for this geometric sequence is 4. So if they want you to do the 5th term and the nth term, you can take care of both of those things just with the formula. The formula for the nth term of a geometric sequence, which is the following. Nth term of a geometric sequence. In other words, you can find any term, the 4th term, the 8th term, the nth term, with this formula. The nth term of a geometric sequence, and that formula is the following. The nth term is the first term multiplied by the common ratio raised up to a power of n minus 1. Okay, so I'm going to get the nth term formula first and then use it to get the 5th term. So specifically using this to get the nth term formula that fits this information, I could put the nth term, but put the specific first term in the information that you were given. And then you would have the R value, which was also given. You want to take any variables that are in this formula and replace it with the given value. So this would be 4 raised up to a power of n minus 1. So this is one of the answers where they were asking for a formula that describes the nth term. Now you can use this formula to get any term you want. So they also asked for the 5th term, so let n be equal to 5 for the 5th term. If you wanted to get the 10th term, you would let n be equal to 10. Then, since I let n be equal to 5 here, anywhere that I see an n, I have to allow it to be equal to 5, and then continue to calculate here. So you have a 5 out here, and then you have 4 raised to a power of 4. And then you can put that right into your calculator, just as you see it. So it'd be 5 times 4 raised up to a power of 4, and you get 1280. Okay, so this is the 5th term. Okay, so of the choices that you have on the practice test, that would have been choice D. It gives you this as the 5th term for choice D, and it gives you this formula right here, 5 times 4 raised up to a power of n minus 1 as the nth term. Okay, so that is choice D for number 34. Okay, moving to 35. In problem 35, with the same set of directions, they give you an A value, which really means they're giving you the first value of -6 and a common ratio of -2. So again, using the nth term formula for geometric sequences. It's just equal to the first term times R to a power of n minus 1, whenever you're talking about geometric sequences. Okay, so let's get more specific here. Let's say that a specific nth term formula using the specific givens that they have offered you is -6 for a sub 1. The r value is -2, and that -2 is being raised to a power of n minus 1. So this is what we call the nth term formula for the geometric sequence. That's one of the things they asked you. Then they asked you to find the fifth term, and you can use this formula to get any term. So fifth term, we're just going to let n be equal to 5. So if using my nth term formula, I'm going to let that little subscript be 5, noting that I am looking for the fifth term. And then n appears here again, so use 5 again. So now this is -2 raised to a power of 4 with -6 as the coefficient. And you can put it in your calculator, but you're going to have to keep this in parentheses this time because it has a negative. So when you put the whole thing in parentheses, you're telling your calculator, raise this negative as well as the 2 to a power of 4. Because if you don't put it in, it's going to come out with the wrong sign. So it's -6 times -2 raised up to a power of 4. And that turns out to be -96. Okay, so that's our fifth term. And this is our general nth term formula. So in problem number 35, these two answers, -96, and this specific nth term formula, -6 times -2 to a power of n minus 1, was choice C. Okay, moving to 36, still under the same set of instructions. This time they give you a is equal to 9, which once again, that is really your first term. So I'm going to label it a sub 1. And your repeating common factor is 1/2. You're asked for the nth term formula. And this is the generic formula for that. You do have to plug in specifics, as I've shown in numbers 34 and 35. And those specifics are the A1 value and the R value. So the nth term for this particular sequence, which starts with a 9 and has a common ratio of 1/2, would be 9 and then 1/2 to a power of n minus 1. So you can get any term in this sequence using that formula. So now I'm going to use it to get to the fifth term, which was the other question that was asked in the instructions for numbers 34, 35, and 36. So the fifth term is 9 times 1/2. I put a 5 there, and I'll also put a 5 here. Anywhere that you see an n, I'm putting a 5. So now this is 1/2 raised to a power of 4 times 9. Again, you can put it in the calculator if you want, or you can do it by hand. You'd have to raise this to a power of 4. 1 to any power is just 1. But I'll write it out anyway. And then you're also going 2 to a power of 4. So this would be equal to 9. 1 to a power of 4 is 1. And then 2 to the power of 4 is 16. Put that in your calculator if you need assistance with it. Okay, then here you're multiplying 9 over 1 times 1 over 16, and it's top times top when you multiply, bottom times bottom. And this is your fifth term. Okay, so the choice for number 36 that had this specific nth term formula and this specific fifth term formula, that would have been choice A. Both of these answers. Okay, moving to 37. Okay, so in problem number 37. Again, we're looking for the fifth term of the geometric sequence. This time they list a sequence of numbers. It goes 1, 2, 4, goes on to 8. And all they're looking for is the fifth term. Now this one, you know, you're already at the third term, and you could see that in this geometric sequence, the R value, the multiplier that gets you from one term to the next and from this term to the next and so on, that is just multiplying by 2. 1 times 2 gets you to this. 2 times 2 gets you to the next term. So that's going to be your R value. So instead of getting into the formula and writing the formula and all that, although let's see if they want you to. I think in 37, all they want you to do is find the fifth term. So they're not asking you to write a formal formula. If you were going out far enough, like if they wanted you to, let's say, do the 30th term or the 20th term or anything that's like past the fifth term, then you probably would want to write the formula. But here, just multiply by 2 to get to the next number. The next number would be 4 times 2, it would be 8. And then the next one after that would be 8 times 2, 16. So this is actually the fifth term. And again, all of these terms are coming from multiplying the previous term by 2. So this times 2 is 8. This times 8 times 2 gives you 16. Okay, so the fifth term is equal to 16. And I just did it by looking at the pattern rather than going the formula route. So that was choice B. Okay, moving to 38. In problem number 38, again, same directions, same type of instructions, only they want the sixth term this time. But like the last problem, number 37, they give you a list. And you're just going to the sixth term. Blah, blah, blah. Okay, now I'm going to get rid of these dots because I'm going to list the fourth, fifth, and sixth term. First, let me see how they're achieving each subsequent term. Let's see. To turn a 1 into a 1/3, you'd have to multiply 1 by 1/3. Because if this is geometric, as it's stated, you're working with geometric sequences here. It's a multiplier, a common multiplier that gets you from one term to the next term. So you should be able to create a 1/9 by multiplying by 1/3 as well. And let's check it out. 1/3 times 1/3 would be top times top is 1. Bottom times bottom is 9. So yes, it does achieve this next term. So now for sure, we know that this is the common R value that's being used each time. So just use it again. So multiplying by 1/3 again, that would be 1 times 1 is 1. 9 times 3, 27. Multiply by 1/3 again, and the next term would be 1 times 1 is 1, and 27 times 3 is 51. Okay, you're up to 1, 2, 3, 4, 5. One more. Hold on 1 second. 27 times 3. Oops, I got that wrong. This is supposed to be, I knew there was a little problem there. So I went to my calculator. So 27 times 3 is 1/81, and then just do it again. Multiply by 1/3, and you get 1 times 1 is 1. And then 81 times 3, I think, is 243. Yep, 243. Okay, so there you go. 1, 2, 3, 4, 5, 6. This is the sixth term in the sequence, which, using the notation that you've been working on, a sub 6 is equal to 1/243. And that is number 36, or 38, excuse me. And that is choice D amongst the choices that you have on your practice test. Okay, moving to 39. In problem 39, the directions change to find the nth term of the geometric sequence when given R is the common ratio. Okay, So they give you A is equal to -4. When they give you that A value, they're really giving you the first value in the sequence. And they say that's -4. And then they say the common ratio in this problem is 1/2. Okay, so they want the nth term of the geometric sequence. So back to that formula that I introduced when I was doing 34, 35, 36, where I was finding the nth term and the fifth term. Here they just want the nth term, which is the first term, times the r value raised up to a power of n minus 1. Okay, so specifically in this problem, any term at all in the sequence, which is called the nth term, any term at all in the sequence is just the first term times r raised up to a power of n minus 1. So you could generate any term at all in the sequence using this starter term and this common ratio. It's just that they don't ask you for anything beyond the nth term. So this is it, your nth term formula, and that is choice B on the practice test. Okay, moving to 40. Problem 40 is the same instructions. Instead of them just giving you the first term and the r value, they leave you to inspect the list of numbers a little bit, and they give you this list, 12, 24, and kind of pick out what you think is the first value and the r value. Okay, so super easy to tell what the first value is. It's the first one in the list right here. This will be a sub 1. And then the common ratio that's being used to get from one term to the next, would be, let's see, you'd have to multiply by 2. Make sure that continues to work as you go down the line. If you take this and multiply it by 2, 12 times 2 does get you to this, 24 times, okay, so definitely the r value is 2. So if you want to come up with the nth term, again, just follow that formula that you see right here in number 39. The nth term is the first term times r raised up to a power of n minus 1. I just keep repeating it, hoping that you'll memorize it. So the nth term is 6 for the first term, 2 for the r value raised up to a power of n minus 1, and that is the nth term formula that will help you find any term at all in the sequence. Okay, then that would have been choice B. Let me make sure. No, that would have been choice D. On your practice test, this answer was offered for choice D. Okay, moving on to 41. So in 41, I believe we moved to some different instructions. They give you, now they've moved on to talk about the sum of a geometric sequence. This goes from the first term to the fifth term. That's what this notation means. Start off by plugging in a 1 into this formula that's out in front of the summation formula. So the formula is 1/3 times 2 raised up to a power of k. Now this looks a little different than what you have seen as you wrote the formula each and every time for a geometric sequence. It was always an a value, then an r value, but the r value always had k minus 1. So you better be careful with this problem and actually list some terms in the sequence so you could tell what the very first term is. If it's in this exact format, where you have the first value and then the r value raised up to a power of some variable minus 1. It could be k minus 1, n minus 1, you know, whatever the variable is that they're using down here. Then you know that if it's in that format, value right here, whether that be, you know, an integer or fraction or whatever, and then an r value, but the power should be n minus 1 rather than what you're seeing here. So let's list some of the values that come from this. So the very first value, I'm going to put some of my work right here. A sub 1 is when you let n be equal to 1. Okay, so that would give you 1/3 times 2 raised up to a power 1, which is just 2 times 1/3 or 2/3. So that's the first term. When you talk about a sub 2, then that's because you're allowing the n value to be 2. N is equal to 2 when you're looking for the second term in the series, it's called now, because this means to add all the terms together, which changes the word to series. So anyway, you have 1/3, and this time it's going to be 2 raised to a power of whatever your k value is, and I guess I should be writing k's here because that's the variable they're using rather than n. I'm just used to seeing an n there, but okay, so now it would be 2 raised to a power of 2. So this would be 4. This time this is 4 times 1/3. So this is 4/3 is the next term. So you've got 2/3, then you've got 4/3. Now we're on to the third term. And, you know, if you're going to sum together all of these terms and you have enough, like I'm going to stop after this third term and let you see what you think is the R value, just to make sure that we're dealing, you know, with this the proper way. So a sub 3, that just means the k value is 3. So this would be 1/3 times 2 raised up to a power of k, and we're using this. So 2 to the third is 8, and then it would just be 8 times 1/3, or just 8/3. So now let's just make sure that what appears to be the R value really is the R value. Okay, if you were to go from here to here, what would you have to multiply this by to get 4/3? I believe just 2. If you multiply this fraction by 2, it would be 2/1 you're multiplying by, and that would give you 4/3. So that checks out. But does it work again? Can you multiply this by 2? You'd be multiplying by 2/1, which would give you 8/3. So that checks out. So since that common multiplier is 2, that would be our R value. Excuse me. Get some water. But what was weird about this is that, like I said, this power was a little bit different than what you're seeing in a geometric sequence. So, you know, when it's not in that exact form, you can't necessarily identify this as a sub 1, the first term in the sequence, and this is R. Now, I know we did get a 2, but look at what the first value turned out to be. It's not just that right there, which, if it's in this format, it is that value right up there, that coefficient. It turned out to be 2/3. So our a sub 1 value is 2/3, not 1/3. And so now we can go on, and you've been asked in number 41 to find the sum of the first n terms. Now you can go on listing them and then add them all together, but you should most definitely know how to use this formula. Okay, so this is the sum of the first n terms. This is when you are summing together a specific number of terms. In other words, the series doesn't spin off into infinity. You are summing together a specific number of terms. Specifically in this problem, we're summing together 5 terms. I just haven't listed them all because I want you to have practice with using the formula that allows you to jump right to the sum just by knowing this and this. It doesn't force you to list the terms separately. I did it because this was not in the exact format of a geometric sequence because it didn't have that k minus 1. So I listed a few of them, made sure what the r value was, and rechecked the first term in the sequence. Okay. So now here is the formula for the sum of the first n terms. First, the sum of the first n terms in a geometric sequence is a sub 1 and then a fraction. 1 minus r to a power of n over just 1 minus r. Okay, so that would be using that formula. First term, that's that. The r value is 2. We're trying to find the sum of the first 5 terms, even though I didn't list them all. So it's 1 minus the r value raised to a power of however many terms you're summing together, which are 5 of them. And then down here, 1 minus r. So be careful as you simplify this. This is going to be equal to the 2/3 that you see out here. Then on the top, you have 1 minus 2 to the 5th, which is 1 minus 32. And on the bottom, you have negative 1. 1 minus 2 is negative 1. So in the end, this ends up being 2/3. 1 minus 32 is negative 31 over negative 1. The negatives cancel out, leaving you with just 31 times 2 over 3. So final answer, 2 times 31, 62 over 3. Kind of running out of room there. So 62 over 3 is your final answer, and I believe that this sum of the first 5 terms, but again, this is how you get the sum of however many terms without listing all of them. But sometimes, it may be a problem that has a little, something or other that you need to inspect, which I already discussed here. Okay, this was choice D, this particular answer. Okay, moving on to 42. Okay, in 42, let's see. Problem 42. Okay, we're under the same instructions. Find the sum. They ask you to go from k is equal to 1 all the way to, let's see, for 42, you're going to n. Now this one is in the same, in the exact notation that we see when we create our own formulas for geometric sequences. It's got the a sub 1 value out here, then the r value right here, raised up to a power of k minus 1. So this is what all the formulas look like when you generate them yourself. This is a sub 1. This is the r value. Okay, so that being the case, if we wanted to come up with the sum of all of the terms created by using this formula, then once again, we would use that summation formula. We're doing it for all terms from 1 to n, so we're not going to a 5th term or a 6th term or a 7th term. We're not summing together 7 terms, let's say, otherwise I would put a 7 here. If we were going to sum together 6 terms, I'd put a 6 here, but we're summing together n terms. They don't tell you what the ending term is, so just leave that as an n. And the formula for that, as I pointed out in number 41, was a sub 1 times 1 minus r to a power of n in your numerator and just 1 minus r in the denominator. Okay, grabbing whatever you do have from this notation here, you can make this more specific to the details in this geometric sum formula. So a sub 1 would be the 5, and you can use this r value to write this as 1 minus r, which is 7, raised to a power of n. That's your numerator. And then on the bottom, you can write 1 minus your r value again, which is 7. That's equal to 5 times 1 minus 7 raised to a power of n. And on the bottom, you have a negative 6. You're going to see often that they are going to separate this fraction. So in other words, this can be written like this. You can write the bottom of this fraction as 1 over negative 6, just as long as you keep that negative 6 in the denominator. And then you can write this top part off to the side. See, they try to get the portion that's just numeric, they try to move it out as a coefficient. It's just a common thing. And then the expression that has the variable in it right here, they separate it out. So you can write this as 2 pieces. It's 1 over negative 6. I just slid that out to the left, and then I slid this numerator to the right. Okay, you can then bring this together as 5 sixths. You can put that negative wherever you want. You can float it to the top, leave it to the side, or put it in the bottom. And then this would be reported off to the side. This is equivalent to this. This is just the more common way that it is typically presented in the software or in the books. Okay, so that is 42, 43. Okay, 43, let's see. 43, 44, and 45, you're determining whether the geometric series, whether the infinite geometric series, because infinite geometric series, when you're finding a sum, because a series is a bunch of numbers that you're summing together. So when you're trying to decide, hey, are you ever going to approach a specific number for your sum? That's called converging. When it converges, that means that you actually can find the sum, even though theoretically it goes on infinitely. When it diverges, that means it does not approach a specific value. It does not get very close to a specific value. So in that case, in other words, it doesn't even have a geometric pattern that's going to converge into a specific value. So there are certain ways that you can tell whether it converges or diverges if it's even a geometric series. You'll have an R value that repeats, and if that R value is, the absolute value of R is less than 1, that means it converges, and you can actually find the sum of the infinite series. So you have an infinite series indicated to you like this, and it goes on and on, meaning it goes off into infinity. So in problem 43, what you're looking for there is, first of all, you want to see if there's a repeating R value in this infinite so-called geometric series. So what you would have to multiply 100 by to turn it into a smaller number 20, well, actually, you'd have to divide this by 5, but that's the same thing as multiplying by 1/5. See? 100 times 1/5 would be 100 over 5, which is 20. You'd have to multiply this 20 by 1/5 to turn it into a 4. See, bring this 20 down here. This would be 20 over 5, or in other words, 20 divided by 5, which would lead you to 4. So the R value, that repeating R value that you use to multiply as you go from term to term, is 1/5. And now let's think about how you tell whether it converges or diverges, because if it converges, then we've been asked in the instructions to find the sum if it converges. So when the R value, absolute value of the R value is less than 1, that means that it converges. Okay, and let me check one thing before I go all the way to the end here. So this is 12.2. Okay, all right, so back to this problem. So we found the R value. That R value, obviously 1/5, absolute value of 1/5 is less than 1. So that checks, which means that this series converges to a particular summation value. And so, because it converges, that gives us permission to find the sum. So the sum of an infinite series is different than what you have seen up here. This is the sum for a geometric series when you are summing a specific number of terms together. They're not indicating in any way that it goes to infinity. This is all about the summation if the series goes to infinity. But again, you need to check that it converges first, or else you can't even find the sum. And when you see that the summation converges and it goes to infinity, then the summation formula is this. Okay, the summation formula from k equal to 1 spins all the way to infinity is just the first terms, pretty easy formula, over 1 minus r. Okay, so my very first term in this sequence was 100, right there, and then 1 minus the r value. So I don't know that you want to bother going to the calculator for this, but you can. You can go 1 minus 1/5, and then hit math, enter, enter, and you will get 4/5 for the bottom. Okay, that'll keep it in fraction form, which is in your best interest because the fractions are super easy to flip over. You float it to the top and flip it over, because division by 4/5 is the same thing as multiplying by its reciprocal, 5/4. So this is no longer here, it's up at the top, and you can continue with the problem. Now it's 100 times 5, 500, divided by 4, and you can put that in the calculator if you don't know what it is, but it's 125. So the sum of this infinite series that goes on and on and on by way of this common multiplier, the sum of that entire series would eventually converge to 125. Okay, that's 43. And 44 and 45 are the same deal. For number 44, let's see what we have here to see if it even is going to happen for us as far as the sum. Okay, now this one doesn't even look like it has a common R value. In other words, 14 times what? 14 times what equals 18? Well, if you wanted to know what that value is that you multiply 14 by to get 18, just solve it like an equation. So really what you're finding here is the R value. Is there a common R value? Well, here this would reduce to 2 goes into the top 9 times, 2 goes into the bottom twice. So 9/2. I don't know that that would work to get from here to here, because you know the same value have to work. So you could ask yourself, same question, to see if it's the same repeating R value. 18 times what equals 20. To get the answer to this, you would just solve it like an equation. So this would be, let's see, 2 goes into the top 10 times. Again, when you're trying to figure out what to multiply this term by to get to the next term, you're really finding the R value, if this really is even an R value. 2 goes into the top 10 times, 2 goes into the bottom 9 times. Notice that these two are not equal. You don't even have the same R values. Or the same, you don't have a common ratio. There is no common ratio here. Therefore, it cannot possibly converge. So this is said to diverge. There is no specific sum that this approaches. And I believe these choices, let's pick choices for 42, 43, and 44. 42 on the practice test, this choice that we came up with, negative 5, 6 times 1 minus 7 to a power of n, that was choice A. For 43, even though I believe you have an answer key attached to your practice test, 43, 125, and it does converge, that was choice B. And then for 44, diverges, that was choice D. And then the last one, let's see if I can squeeze it in here. For 45, it gives you another series that goes from 1 to infinity. There is a 4 right here, a 2/3 here, so this is exactly in geometric form notation. It's got a power of k minus 1 like the formula states. It's got the a sub 1 value here, the r value here. So you can already tell because it's in the perfect, form that of the formula that we use to get geometric nth term formulas. So this particular r value, which is 2/3, its absolute value is less than 1. Therefore, these 3 dots shaped like a triangle mean therefore the series, the summation series, converges. And therefore, I have permission to find the sum. Sorry, I didn't let you see that. Let me scoop this up. This was number 45. This is how the problem started, that you're summing all the terms created through this geometric formula here. And I know this is in geometric because the formula that we used to create all our geometric formulas was a sub 1 times the common ratio r, always raised up to a power of k minus 1, which makes it easy to identify the first term, the r value, and so forth. So I took this r value. It does pass the test of being less than 1. Therefore, I know it converges, and therefore I have permission. That means that the summation does exist for this infinite series. Okay, so when you're going to go and find the summation here, the summation for an infinite series is said to follow this formula, a sub 1 over 1 minus r. So nice easy formula when you're trying to find the summation for an infinite series that converges. Okay, the very first term is that 4, and then it's 1 minus r. Again, you can put the bottom in the calculator if you want, but this is just 3/3 minus 2/3. 1 is equivalent to 3/3. So you have a 1/3 on the bottom. If you put it in your calculator, it's going to give you the same thing. And then here you have a 4. If you want to simplify this by hand, it's quicker than putting it in the calculator. Just float to the top and flip that divisor over. So this is no longer here. It's up at the top, acting as the reciprocal. 4 times 3 is 12. And that particular choice, and the fact that we've stated that it converges on the practice test, that was choice B. Okay, that takes you all the way through 45. And then I believe that there are 48 problems. I will continue with, let's see, I guess I can do that actually right now. No, I think I'm going to save this because these are kind of long. I'm going to do this last little short video in the next video. I'm going to stop this one here. That takes us all the way up through 12.3, and in the last video, I'll do 46, 47, and 48 from section 12.5.